All right, 3-3, nuclear chem. So we've got alpha decay, beta decay, and gamma decay. You should know the difference between the two. You are going to have that little chart when you're taking the exam. It'll be there, but you should still have an idea about each one of the equations. Now, in alpha decay, an unstable nucleus emits a helium nuclei. It's 2 protons, 2 neutrons. They basically pop out, and the mass number goes down by 4, and the atomic number goes down by 2, because 2 of the things that pop out are protons. So, remember polonium. Alexander Levenko ended up getting poisoned. He ingested through some tea that was poisoned. He ingested polonium, which has a mass of 210 and an atomic number of 84. So once the polonium ended up inside his body, it started decaying. Well, it was decaying anyways, but the part that was damaging was when it got into his body. And as polonium decayed, the 4 particles popped out. So the 210 went down to 206. 2 of those particles were protons. So the 84 went down to 82. That is lead. So lead was left in his body along with these little tiny alpha particles, these little helium nuclei. So the 204 plus the 4 is 210, the 82 plus the 2 is 84, and this is what wreaked havoc on the DNA and basically shut down his body, and he died shortly after that. So here's one example of the alpha decay that takes place when a substance releases a helium particle. Beta decay. Beta decay is when you, again, have an unstable nucleus. There's too many protons, or too many neutrons, not enough protons, and that ratio is off. So if you look at carbon 14, carbon 14 has 14 particles. 6 of them are protons, and 8 of them are neutrons. And remember, they like the 1-to-1 ratio. This is not a 1-to-1 ratio. So there's a little bit extra on the neutron side. So one of these little guys says, I'm not going to be a neutron anymore. I'm going to be a proton. So it goes from 8 neutrons down to 7 neutrons, 6 protons up to 7 protons, because one of these neutrons flips and becomes a proton. Now when it becomes a proton, it's positive. The negative portion of it, I guess, the little tiny negative electron pops out. And that's what we call our beta particles here. So the atomic number goes up by 1, because we have 1 more proton now. The mass number stays the same, because the number of protons goes up, but the neutrons goes down. So overall, it's a wash. So 14 stays 14, and out pops this high energy electron, this little itty bitty guy that moves faster and farther than the big alpha particle, and it can penetrate a little bit further. Now we write the Greek symbol beta, and then we put, instead of a 1 here, which would indicate a proton, atomic number 1, we put a -1 that indicates an electron. And electrons have no mass, so we put a 0 up there. So that's our beta decay. And finally, gamma decay. This is the easiest of all 3 of them, because nothing changes except for the amount of energy that it has. And I give the example of a hyped up dog. He hasn't seen you in a couple days, or you went on vacation or something. You come home, you let your dog outside. The dog runs around and comes back inside. He's still the same dog, but he has less energy. The energy was released outside. So nothing changes here except for the energy, and this is high energy with a lot of penetrating power and very dangerous. Explain what an isotope's half-life is. Half-life is how long it takes for half the sample to decay into something that's more stable. So we can work out these half-life problems. I'll give you this chart. You just have to know what to do with it. What I recommend is always starting with 0 and the mass that you're given in the problem. It says, how long will it take for a 20-gram sample to decay? So start with that always. Always put a 0 in the time pass slot in the beginning, and you know you have your complete sample. If this was percent, you would start with 100%. You have all of it. This problem's not dealing with percent, so I'll erase that. But if you did have a problem that dealt with percent, you would treat it exactly the same way. You would just start with 100% instead of a mass. Now, how long will it take for a sample to decay to a 2.5 gram sample if an isotope's half-life is 5 minutes? So we'll worry about the 5-minute business in a minute, but let's start with how many half-lives it takes to get to 2.5 grams. So 20 grams, first half-life passes, now we're down to 10 grams. Second half-life passes. Now we're down to 5. Third half-life passes. Now we're down to 2.5. So it takes 3 half-lives. Now what's 3 half-lives? You can do 3 times each half-life is 5, and you can say it's 15 minutes, or you can use the chart. You can say the first half-life means 5 minutes has passed. After the second half-life has passed, that means 5 plus 5, that's 10 minutes have passed. The third half-life, yet another 5 minutes has passed. Now we're up to 15 minutes. So 15 minutes to get it to 2.5, which is the same thing we did here. Next problem. How much will remain of a 100-gram sample after 5 half-lives have passed? So we start with no time passing and our entire sample, 100 grams. After the first half-life has passed, we're down to 50. After the second half-life, we're down to 25. After the third half-life's passed, we're down to 12.5. The fourth half-life, we're now down to 6.25. And finally, after the fifth half-life has passed, we're down to 3.125. So after 5 half-lives, we have 3.125 grams left. Now notice that problem didn't give you any information about how long a half-life is. It didn't say it's 5 minutes or 432 years or anything like that. It just said what mass is left after 5 half-lives. So don't go crazy filling out the whole chart if you don't need to. Notice I stopped over here after the third half-life. I didn't need to do 4 or 5. That's just a waste of time. So manage your time wisely on the exam. All right. List 4 actions that could increase your exposure to radiation. Hopefully you listed something like being on an airplane quite a bit. You're up at a higher altitude, more exposure to radiation from the sun. Smoke detectors. I remember we talked about how they worked. Being treated through nuclear medicine. Obviously they're injecting you with radioactive isotopes. Living at high altitudes, same idea as a flight, not as much obviously. And high levels of radon in the basement. And the one thing we didn't talk about, and it's my bad, I should have, smoking. Smoking is the #1 way to be exposed to radiation. Crazy, crazy amount of smoke that you receive or a crazy amount of radiation that you receive when smoking just plain old cigarettes. Nuclear fission and fusion. Fission, the nucleus of a larger atom is split. Okay. Fusion, we fuse 2 together, so it becomes a larger nucleus. We split it, we get smaller, and fusion, we get larger. Fission, this is what we typically see whenever we talk about nuclear reactors. Fusion, this would be ideal because it produces so much energy, it's efficient, but we need ridiculously high temps, which are hard to handle, and you should also know this is what happens in the sun. In the sun, we take 4 hydrogens and fuse them to get 1 helium. And that ties into Einstein's equation, which we could jump to right now. When smaller nuclei fuse, total mass of the new larger nucleus is a little less. So if I add up 4 hydrogens and I fuse them to get, oops, that changes, 1 helium, the mass of this is a little bit more, and this is a little bit less. So where did the extra mass go? It turned into energy. And that's a crazy amount of energy that we receive from the sun. Large, large, large amounts of energy. All right, 2 reasons why water is absolute necessity in a power plant. Hopefully you mentioned one of these, or at least 2 of these 3. 1, we want the water to absorb any neutrons. 2, we put the spent fuel rods in the water, and it can cool them down and absorb any extra neutrons that are coming out, so it doesn't perpetuate the reaction. And we also use the water to cool the reactor core so it doesn't heat. And finally, and I can't believe I didn't put this in there, that's the whole point of a nuclear power plant, is to produce electricity. So the water heats up. Remember, we pump water around the nuclear core. The water gets hot and it turns to steam, and the steam spins the turbine. And when the turbine spins, it ends up producing the electricity that then goes out and through the wires and so forth and right to your home. So we've got to put water around the nuclear core. We want it to get hot. We want it to turn into steam. We want that steam to expand and spin the turbine, and then that will cause electricity to flow. And finally, radon. Before you buy a new home, you should make sure that it doesn't have high levels of radon, because radon gets into the basement of the houses and it can lead to cancer. Especially lung cancer. So usually you won't get a mortgage unless the radon has been tested, and if it is high, you need to reduce the amount of radon somehow. Usually just installing a mitigation system, which is like a fan that draws the radon out and up along the side of the house, by the chimney usually, and up and out. And that makes it safe in your basement. But it seeps through the rocks from the uranium decaying naturally. And like I said, it is dangerous because it does cause lung cancer.